Good morning, everybody. It's Tuesday. Another fine day here in Central New York. Hope everyone's doing well. Let's see what's going on with me. Needed coffee this morning. Well, I need coffee every morning, but this morning I'm running on empty for some reason. Let's see. People have been sending me some videos and some notes on what you're doing. Sounds like you guys are really busy. Makes me miss you guys even more, but it's really good to hear from you. So if you haven't sent me a note and you get a chance, just let me know what you're doing, how you're doing, what's going on, that kind of stuff. Let's see what's going on here. Oh, I finally finished my niece's dollhouse yesterday. I'll send you some pictures. Came out pretty good. I finished that last night. Schoolwork is kicking my butt, so I've been basically up at 6 and working till 2 or 3 every day, and then trying to get some grading done. So school is crazy busy, but hopefully it's working out for you. Maybe we should talk a little bit about the rest of the week, just to make sure we're all on the same page. So today we're going to be working on more acid-base stuff. Actually, it's more Equilibria stuff. It's not even really acid-base stuff. So we're going to run through some of that today. We should finish notes tomorrow. I'm giving you Thursday off, and then the unit test is going to be on Friday, and I think I said it starts at 9. All right, so make sure you're making plans for that. The titration lab, I believe, is due on Monday. That should be the plan for the week. I do have a SUPA meeting with SU today, this afternoon. I'm not sure exactly what they're going to be talking about. Probably more about the final, which is actually coming pretty quick. So as I learn more, I will let you know, right? So my plan is to keep going through material at the pace that we're going, and when we're done, we're done. So if we're, my original plan was really to be done with material really as we went into June early, because originally you guys were all going to be doing a lot of that senior stuff. So my plan was to be pretty much done with everything except for the final exam by June. And really we're on target to do that. When we're done, we're done. And I'm sure that's going to make a lot of you happy, because we'll be done the beginning of June, I really think. All right. So, and if that's the case and we don't go back to school, we'll get the final done and you guys will be done with me. All right, so that's kind of the plan. And that'll develop as we go. Okay. So we do, I think, have a pretty long lecture today. Some of it actually is a little bit of review. We've done a little bit of this stuff, so I did some extra stuff in Equilibrium that the textbook puts here. All right, so we're going to do a little bit of review on some solubility stuff, and we'll get into some new things. So today, let's entitle this Solubility Equilibria. And we're going to talk about the solubility product constant. And we've already talked about this. Okay, so it's an equilibrium constant, and it is KSP. Okay, it's an equilibrium constant, and SP stands for solubility product. So let's say we have NaCl solid, And we're going to dissolve that in water. Well, it forms an equilibrium, and this is an ionic compound. It's salt, so it'll almost completely ionize, and we will get Na plus aqueous and Cl minus aqueous. Well, this has an equilibrium constant for this dissolving. In this case, it's going to be pretty large because it's going to go all the way to the right. Right, so this completely ionizes. So the equilibrium is going to sit way over here. There's not going to be much salt left. Right? Now, KSP for this would equal the concentration of Na plus aqueous times the concentration of Cl minus aqueous. This is a solid, so it doesn't matter. Okay, its concentration doesn't really change. So there's our KSP equation. Now, in general, the solubility product or our KSP of a compound equals the concentration of the ions raised to the power of its coefficient in the equilibrium equation. And again, this is nothing new. So let's say we have CaF2 solid dissolving, forming Ca plus 2 aqueous, and 2F minus 1 aqueous. Okay. Our KSP, or our solubility product, would equal the concentration of Ca plus 2 aqueous times the concentration of F1 aqueous squared. Right, so this would be our KSP equation. So I just kind of want to run through that with you again. Now, the solubility product constant and the solubility of the substance are actually two different things. Difference between solubility and KSP, or our solubility constant. We're talking about solubility. Solubility is the amount that dissolves in a specific amount of solvent at a specific temperature to form a saturated solution. And usually we measure this in grams per liter. Well, there's also molar solubility. Which is the number of moles of solute that will dissolve in 1 liter of solution. So this is moles per liter, which is really what? Molarity. Now, solubility really changes. And that's really what's kind of important here. Solubility really changes depending on some factors. You know, for example, temperature plays a major role. Okay. Generally, as temperature increases, solids are more soluble. It's the exact opposite for gases. Generally, as temperature increases, gases are less soluble. Right, so temperature is one thing. pH often plays a role, right? Which is why this is kind of being talked about here again. Common ion, which we've already talked about, plays a role in solubility. Okay, and we'll talk a little bit about this as we go. So the solubility does have a lot of different ways that it changes. Our KSP or our solubility product constant this is an equilibrium constant. That forms from the solid to the saturated solution. KSP is a constant. At specific temperature. And does not change. The larger the KSP, the more it will dissolve. Just like our other equilibrium constants, the larger it is, the more the products are favored, the more it's going to push it to the product side. All right, so let's play some games mathematically with this. Ag2CrO4 solid is added to pure H2O at 25 degrees C at equilibrium. Concentration of Ag plus aqueous is equal to 1.3 times 10 to the minus 4th molar. Calculate KSP for this compound. Now in this problem, we're going to make some assumptions. Right, so remember we have acidic, basic, and neutral salts. All right, so in this problem, we're going to assume that the salt that's dissolving does not have an effect with the water molecules. All right, so we're just going to assume that because it doesn't give us any information on that. All right, so we're going to assume that it doesn't react with the water molecules. We're going to assume since we have pure water, there's nothing already dissolved in there. So this actually becomes a pretty straightforward problem. All right, so we need to write our equation. So we know that we have Ag2CrO4 solid. And this is going to go to an equilibrium. And we get 2Ag plus aqueous plus CrO4 minus 2 aqueous. Right? So we come to equilibrium, which means the solution is saturated. Right? And we've measured the amount of Ag plus we have in the solution. Now, let's quick look at this stoichiometrically. For every 1 mole of this, we will get 2 moles of this and 1 mole of this. Well, it gives us this concentration. So we know that silver is 1.3 times 10 to the minus 4th molar. Okay. So if this is the concentration of the Ag, now we can figure out what the concentration of this is. Because for every 2 of this, we get 1 of this. So the concentration of CrO4 minus 2 is going to be half of whatever the Ag plus is. So we're going to divide this by 2. And that will give us the amount of CrO4 minus. So we have 6.5 times 10 to the minus 5th molar. All right, so this is my concentration of CrO4 minus 2. Well, now that I have those concentrations, we know that KSP is going to equal the concentration of Ag plus squared times the concentration of CrO4 minus 2. And it just becomes a substitution. 1.3 times 10 to the minus 4th squared times 6.5 times 10 to the minus 5th. So the KSP for this is 1.1 times 10 to the minus 12th. Now, what is this telling me? Well, this is a very small number. It's a really small number, which means Ag2CrO4 is not very soluble. Okay. The equilibrium lies over here. Very little of this is actually produced. Okay, so this is really an unsoluble salt. Right, but we can look at its KSP and calculate it to prove that that is so. All right, so let's try another problem. And this is similar to one that we've done before. The KSP for CaF2 is 3.9 times 10 to the minus 11th at 25 degrees C. By the way, I think in the textbook, I think there in the back, there are lists of KSPs. I'm pretty sure there's an appendix and there's lists of KSPs back there. All right, just in case you need them in a textbook problem. Calculate the solubility of CaF2 in grams per liter. All right, well, what are we going to do with this thing? Well, let's start by writing our equation. We have CaF2 solid. Okay, it's going to dissolve and come to equilibrium. It's going to break into Ca plus 2 aqueous and 2 F minus 1 aqueous. So what are we going to do with this? Well, guess what we're right back to. This is an ice table. This is a solid. Its concentration isn't changing, so we don't need that. All right. We're starting with none of this. We have none of the ions to start with before we dissolving. All right, so that means these are going to go up by, that's going to go up by x. This is going to go up by 2x. Okay, so at equilibrium, this is x, and this is 2x. KSP is equal to the concentration of Ca plus 2 times the concentration of F minus 1 squared. We can substitute in. We know our KSP is 3.9 times 10 to the minus 11th is equal to x times 2x squared. So we start doing some algebra here, and we got 3.9 times 10 to the minus 11th equal to 4x cubed. So when we do this math, x is actually equal to the cube root of 3.9 times 10 to the minus 11th all over 4. Okay, so x is equal to 2.1 times 10 to the minus 4th moles per liter, or molar. Okay. So this is the concentration of Ca plus 2 So this is the concentration of Ca plus 2. But if we look back up here, all right, if we look at the stoichiometry, for every one of these, we get one of these. All right, so we know that CaF2 will dissolve 2.1 times 10 to the minus 4th moles in a liter of water. All right, so this all comes from CaF2 in a 1-to-1 ratio. So we now know that we had 2.1 times 10 to the minus 4th moles of CaF2 in 1 liter of water. Now, I don't want this in moles per liter. I want it in grams per liter. So okay, I'm going to have to calculate GFM. And we want in 1 mole of CaF2, there are 78.1 grams of CaF2. And this cancels. And it turns out that we have 1.6 times 10 to the minus 2 grams per liter. Right, and that would be our solubility of that salt in grams per liter. Right? And we've done something like that in the past. Nothing new really there. All right, so let's talk a little bit about some factors that affect solubility. And the first one we're going to talk about is our common ion effect. And again, this is something we've actually already talked about. So if there's a commonality in the solution, if there is a common ion already in the solution, solubility decreases. Okay, so we've actually already done this. All right, so let's actually calculate a problem with this. Calculate the molar solubility of CaF2. Our KSP is equal to 3.9 times 10 to the minus 11 in a solution that is 0.020 molar in CaNO3 2. So in other words, we have a solution of calcium nitrate. Okay, and we're going to try to dissolve some calcium fluoride into that solution. Well, we have a common ion, right? So we got CAs already dissolved in that solution. That's going to affect how much of this is going to dissolve. Right, now, this is a salt. Okay, it will completely dissolve. So if it completely dissolves, right, and this is this compound is 0.20 molar, that means using stoichiometry, the concentration of Ca plus 2 is going to have the same molarity, 0.020 molar. All right, I hope everyone understands that at this point. Right, so we know our concentration of Ca plus 2 to start. So we have a common ion. So our equation that we're trying to do is we're trying to dissolve CaF2 solid to produce Ca plus 2 aqueous and 2F minus 1 aqueous. Again, this is an ice problem. We're just starting in a different place. And we've actually already done a problem similar to this in the past. Okay. So, again, in our equilibrium, this doesn't matter because it's a solid. Concentration doesn't change. Right? But we're starting this time. Last time we started with none of this. Right? And this time we're starting with some calcium already in there. And that's going to change our equilibrium. So we're starting with 0.020 molar here. Okay, and none of that. This is going to go up by x. This is going to go up by 2x. So that means my concentration is 0.020 plus x and 2x. Our KSP, we've already calculated and say it's Ca plus 2 times the concentration of F minus 1 squared. All right, we know the KSP is 3.9 times 10 to the minus 11th. Now let's just write this out. So then my Ca would be 0.020 plus x times 2x squared. Now here's my question for you. Okay, we've already worked with this compound. Okay, did we say that this is is this soluble or an insoluble compound really? Well, our KSP is 3.9 times 10 to the minus 11th. It's extremely small. So are we going to make any of this really? Is this going to change much anyways? Are we going to make much more x? And the answer is no. All right, so we're going to make an assumption. So we can assume very little CaF2 will dissolve. So we're going to assume that 0.020 plus x is really just going to equal 0.020 molar. Okay, we're going to make that assumption, and we'll check it later on. All right, we'll check it at the end just to make sure. All right, but we're going to make that assumption. So this is going to change to 3.9 times 10 to the minus 11th equals 0.020 times 2x squared. And when we do this math, x ends up equaling 2.2 times 10 to the minus 5th molar, or moles per liter. So that is our molar solubility. All right, now let's just check it. So if we do 0.020 plus 2.2 times 10 to the minus 5th, what do we get? Well, with sig figs, we still get 0.020. Right, so was our assumption correct? And the answer was, so we're okay with that. We're good with this. All right, so now, what happened to our solubility when we had that common ion in there? Well, the molar solubility without it from the last problem was 2.1 times 10 to the minus 4th molar. All right, so when we already had that salt in there, less will dissolve. All right, so our common ion interferes with the dissolving of this, right, and it will dissolve less in that solution. Good. All right, so let's look at solubility and pH. This is a little bit more complicated than those, though. So in general, slightly soluble salts that have basic anions increases as the solution becomes more acidic, or as my pH decreases, or as concentration of H plus increases. Okay, so in general, slightly soluble salts with that basic anion, okay, the solubility, they'll be more soluble the more acidic we are. Question is why? The H plus ion in the acid, okay, so this is a acidic solution. The H plus ion will react with the basic anion, which will decrease its concentration. So CaF2 solid dissolves and it forms Ca plus 2 aqueous and F minus 1 aqueous. Well, this is the conjugate base of a weak acid. Okay, so HF is a weak acid. This is its conjugate base. All right, so this is a basic anion. So if we dissolve CaF2 in an acidic solution, the F minus will react with the H plus in the solution. So the F minus will react with the H plus and it will form its own equilibrium with HF. So we have this acidic solution. Again, we have two different things that are going to happen in the solution. All right, so in that acidic solution, we try to dissolve some CaF2. So it dissolves, and then immediately once we start forming, this should be a 2 here, sorry. As soon as we start forming this F minus 1, that F minus 1 then reacts with the H plus that's in the solution, right, and it forms an equilibrium with HF. Now, the more acidic the solution, what does that mean if it's more acidic? Right? Well, if it's more acidic, we have more and more and more and more and more of H plus. So the more acidic the solution, the more H plus we have, the more F minus that reacts. Well, okay. What does that have to do with this equation that's happening up here? Right. So now, let's go back and talk about equilibrium. If we use Le Chatelier's principle, right, so this is at equilibrium. If we stress this, okay, in other words, let's take this F minus 1 away. Does it like that? Okay, no, it's going to shift the equation to the right. In other words, it wants to replace the F minus 1. So to replace it, that means this solid is going to dissolve more of it. So now we have two different things. So what happens is this dissolves, and then the F minus 1 reacts with the H plus to produce HF. And as that does, this is gone again. So what happens? This dissolves more, and the F reacts with the H plus and produces HF. All right, once this is gone again, it produces more. All right, now eventually it'll stop because we'll run out of H plus. All right, but the more H plus we have, the more of this is going to come over here, and then the more of that that's going to come over here. Okay, I hope that kind of makes sense. So let's see if we can kind of write that. CaF2 solid is in equilibrium with Ca plus 2 aqueous and 2F minus aqueous. So this right here reacts with H plus, okay, which means it's gone, which means this whole thing shifts to the right. Which means more CaF2 dissolves. Now, as the pH decreases, more CaF2 will dissolve. Okay. So that's the theory behind what's happening here, right? It's kind of based on Le Chatelier's principle. All right, so now we have to do a couple problems with this. What is the molar solubility of MgOH2 in a solution that is buffered to a pH of 11? KSP is equal to 1.8 times 10 to the minus 11th. So we are going to dissolve MgOH2 in a basic solution that's buffered. Now, what does that mean? What does buffered mean? Well, what does a buffer do to the solution? It resists pH change. So if our solution is buffered, okay, it's going to resist the change in the concentration of H plus or OH minus. And that's going to be important in this equation, all right? So you need to make sure, all right, that you understand what's happening here. Will resist pH change. All right, now, we can actually calculate the concentration of OH minus in this solution, all right? So we need the concentration of the solution before we actually get started. So our concentration of OH minus in the solution, why OH minus, by the way? Because that's our common ion. All right, our OH minus concentration is, we know that pH plus POH equals 14.00. So that means our POH is equal to 3.00. All right, we can calculate our concentration of OH minus. All right, so our concentration of OH minus is going to equal 10 to the minus POH. So the concentration of OH minus is equal to 1.0 times 10 to the minus third molar. So that's the concentration of OH minus already in the solution. Now, because it is a buffered, because it's buffered, the concentration of OH minus is not really going to change when we add MgOH2. Now the equilibrium equation for the dissolving of MgOH2, and hopefully you can do this now, KSP is going to equal the concentration of Mg plus 2 times the concentration of OH minus squared. Okay. So now, we know this is a buffered solution, so when we add the MgOH2, this concentration is going to stay the same. This will not change. Okay, so if we know what this concentration is going to be, and we know what the KSP is going to be, we can figure out the concentration of the Mg plus 2. This is 1.8 times 10 to the minus 11th equals the concentration of Mg plus 2 times 1.0 times 10 to the minus third squared. So the concentration of Mg plus 2 is equal to 1.8 times 10 to the minus 5th molar. There's my molar solubility of MgOH2. Okay. This is at a pH of 11. Well, what's going to happen to this number if we put it in a different pH? Will it change? And the answer is yes. Let's see how it changes. What if the solution was buffered to a pH of 9? Now, what should happen? Right? We said that the more acidic it is, the more that should dissolve. Okay, so we said the more acidic the solution, the more it should dissolve. Okay. So this should be a bigger number because we're going down the pH scale. All right, so we're going to do the same exact thing that we did up here. All right, so our concentration of OH minus is a little bit different because we have a different pH. Right, so pH plus POH equals 14.00. So our POH is equal to 5.00. So the concentration of OH minus is equal to 1.0 times 10 to the minus 5th molar. We're going to do the same assumptions up here. Our KSP is equal to the concentration of Mg plus 2 times the concentration of OH minus squared. Right, we're going to assume this stays constant because we're buffered. So then we have 1.8 times 10 to the minus 11th equal to the concentration of Mg plus 2 times 1.0 times 10 to the minus 5th molar squared. And the concentration of the molar concentration this time is now 0.18 molar. So let's compare. At a pH of 11, at a pH of 11, okay, it would dissolve 1.8 times 10 to the minus 5th moles per liter. At a pH of 9, it dissolves 0.18 moles per liter. All right, big difference. Okay, so if I needed to get this dissolved into a solution, I'm going to make it an acidic solution. Okay, we're gonna keep going. I know it's getting to be a long video, but let's do complex ion formation and then we'll stop. All right, so we'll do this and then we'll stop and we'll finish up next class. Okay, so first of all, what's a complex ion? A complex ion is a metal ion with a Lewis base bonded to it. Okay. Remember, a Lewis base is a proton pair donor. A Lewis base is a proton pair donor. Now, complex ions are very soluble in water. Right, So let me show you an example of a complex ion. So if I have in solution, let's say I have some Ag plus in solution, aqueous. Right, and in that solution I also have some ammonia, which is actually a Lewis base. Okay, why is it a Lewis base? Because it has these two pairs of electrons that are sitting here that it will donate to and share with another atom. So if I have this in solution, what happens is this is going to come over here and start sharing with that, and that's going to come over here and start sharing with that, and we end up with something like this. Oops. Ag okay, so the ammonia starts sharing these pairs of electrons with the silver, and the silver shares these electrons here, so you get this big ion, right? So this whole thing is an ion, and it's got a +1 charge. So this thing right here is what's called a complex ion. And for complex ions, we're going to use an equilibrium constant also, except we're going to use Kf. And this is called the formation constant. It's called the formation constant. Now, let's put this, what we just drew, into a chemical equation. So we had Ag plus aqueous, and we added 2 NH3 aqueous. And this is actually going to form an equilibrium with Ag NH3 2 aqueous. That's our complex ion. Well, we can write an equilibrium expression for this called Kf. Hopefully you can do this. So Kf is equal to the concentration of our product NH, not O, divided by the concentration of our reactants, Ag plus and NH3 squared. Okay, so this is my Kf. Now, let's just think about this. Okay, let's just look at this mathematically. So, if lots and lots and lots of this forms, so if this number is really big, that means these numbers are really small, which means we're going to have a large Kf. So when these two come together, if we make lots and lots of this, okay, that means it's going to be a stable complex. So the larger the Kf, the more stable the complex ion. Now, what if very little amount of the complex ion forms? So if this number is small, these numbers are big, that means my Kf is small. That means my complex is not stable. So the larger Kf is, the more stable the complex ion. Okay, so let's write, we've got one page left. It's not even a page. Let's write a couple things. If the interaction between the metal ion and Lewis base are stronger than the interactions between water and the metal ion, then you will be able to dissolve more of the salt that has the metal ion. That's a lot. If the interaction between the metal ion and the Lewis base are stronger than the interactions between the water and the metal ion, then you'll be able to dissolve more of the salt that has the metal ion. Let's see if I can show you this. All right, I want to show you with pictures. All right, so now let's say that we want to dissolve silver chloride. So AgCl solid. Okay, and we're going to dissolve that in H2O. And it produces Ag plus 1 aqueous and Cl minus 1 aqueous. Right, so the Ag, okay, is actually going to dissolve by molecule ion attraction. And when this happens, okay, right, our Ag ion gets surrounded by the water molecule. And the Cl minus ion does too. Right, so this is our molecule ion attraction. So this is our solution. Now, what if there was some ammonia in this solution? Okay, so just for fun, let's say we had some ammonia in here. Well, the ammonia is not going to be attracted here. So we get these two electrons it wants to share. This doesn't want any more electrons. Okay, so the chlorine is not going to be affected, but this one is going to be affected. Now, if, and only if, the attraction between the ammonia or this Lewis base is stronger than the attraction between the water, we form a complex ion. Now, if the attraction between the ion and the water is greater than the attraction between the Lewis base and the ion, nothing happens. All right, but if the attraction is stronger than the water attraction, right, it kicks the waters off. So if the Lewis base has a stronger affinity for this ion, the water molecules are kicked off. See ya. Wouldn't want to be ya. Bye-bye. And the complex ion forms. Right, so this forms the complex, oops, this is an Ag. This forms the complex ion. And so there's our ion that forms. And then, not only that, now we have extra water. And what do those water molecules do? Well, they're going to go right back, and they're going to dissolve more silver chloride. Okay. So we have those extra water molecules that can go back and dissolve more of the solid. Okay. So now let's see if we can add some words here. So when we add our ammonia to the solution, the Ag plus 1 ion reacts with two of the NH3 ion molecules to produce our AgNO3 NH3 2 complex ion. This is a plus 1. Okay, so now the Ag plus 1. So this is one equation that's happening when we add the ammonia. But remember, our original equation was AgCl solid dissolving to form Ag plus 1 and Cl minus 1. This is another Le Chatelier issue. All right, so this is the first thing that happens. We have AgCl going to Ag plus 1 and Cl minus 1. Then we add our ammonia. What does the ammonia do? It takes this Ag plus 1, it reacts with NH3 to produce our complex ion. So now this is gone. Okay, what does this want to do to fix that problem? Okay, well, if this is gone, if the Ag plus 1 is gone, in other words, it's used up to form the complex ion, the reaction will shift right. If the reaction shifts right, that means more of the salt will dissolve. More of the salt will dissolve. All right, so this again is a Le Chatelier issue. All right, and you can do similar problems to this as we just did with pH. Okay, and we could use our KSP and do some calculations with that too. So you could do really similar calculations with this. All right, but this is what a complex ion is. Now remember, right, what's important is that the attraction between the Lewis base and the metal ion has to be greater than the attraction than the water and the metal ion. Right? So if this attraction is stronger than this attraction, none of this happens. Okay, none of this happens. But if the Lewis base has a stronger affinity to the metal ion than the water does, then this solubility change will change. Okay, that's where we're going to stop for today. We will finish up tomorrow, and have a good afternoon.